This project is construction of a reflector for the headlight on my little motorcycle. I'll form the reflector using hydraulic pressure, the same process that I used for building the signal light and spotlight buckets. I started by building a 1/2 inch thick steel die and clamp. The die aperture is the right size for the reflector. This edge has a smooth fillet so it won't tear the material. The material I'm using is 24 gauge type 321 stainless steel. The clamp may look like a bit of overkill, but let's do a little bit of arithmetic. The diameter is 3.5 inches. That means the area is 9.6 inches. My grease gun is rated at 1500 psi. So there's a potential 14,000 pounds of pressure we're going to be exerting on this clamp. I locate my holes in the workpiece by simply drilling through the flange. Before I start deforming material, let's talk briefly about the mechanical properties of material. If I wind a string onto a guitar, there comes a point at which it starts creating a musical note. That's also the point at which it starts yielding or stretching. If I continue applying more and more force to the end of the string, eventually we'll reach its ultimate strength, which is where the string fails. That is its ultimate strength. Now let's compare three fairly common materials: 3140 carbon steel, 2024 aluminum, and 321 stainless steel. The yield strength of the carbon steel is 91,000 pounds per square inch. The ultimate strength is 104. The yield strength of 2024 aluminum is 50, and its ultimate strength is 76. You can see the gap here is quite a bit more than it is here. 321 stainless, on the other hand, the yield strength is 35 and the ultimate strength is 90. Now that's a big difference. This is not the elastic modulus of the material, but it gives you a pretty good indication of how far you can stretch it before it lets go, like that guitar string did, and sprays grease all over the inside of the workshop. Okay, back to the fun stuff. The base of my hydroforming machine is basically a slab of steel with threaded holes and a tunnel that exits at the center of the plate and a grease zerk. The smooth fillet on the clamping plate or die goes down. On previous jobs, I found that with a diameter of 2 inches, I could raise it 1 inch before the explosion. This project, I have a diameter of 3.5 inches, and I want to raise it 1.25 inches, so I should be safe. I've put a dial indicator on it for the first few strokes, so you can have the satisfaction of seeing it move. About all that's left is to clean up the mess. Now let's have a look and see what happened inside. This is a line that I drew on the base before forming. The holes are all stretched to an elongated shape. Notice the scalloping along the edges where material has been borrowed from here to pull up into the dome. Except for a narrow band of polishing where the borrowed material skidded over the fillet, there are no tooling marks on the inside and no tooling marks on the outside. The surface will polish up quite nicely with a hard rubber disc on a Dremel.